Thanks everybody for coming. So I'm going to be talking about infrastructure strategies and innovation in the AI area. I have to do a little bit of off the cuff here because I always make fun of my boss, especially when he does keynotes. So this is not a Christmas carol. There's no happy warm message at the end, right? I'm not going to tell. This is if you like data, this is your Christmas carol. It's gonna be very data heavy. I'm going to try to get through everything. I practice this. There's a lot of data here, so I will go as fast as I can to try to have time for questions. But if we don't, please come talk to me at the booth. I'd love to talk to you more about anything infrastructure and AI related. So, like I mentioned, my name is Daven Winans. Who is this guy? I'm the Vice President of Engineering and Innovation at US Signal. Started my life in the managed services provider space, did a brief, horrific 8-year stint in healthcare, and have been with US Signal, which is a cloud service provider, for the last decade. So I usually joke that I've run every technical team at US Signal in that 10 years. It is not a joke, though. It is actually true. So right now, mainly in the network engineering, transport engineering, cloud engineering space, and then obviously our innovation team. That QR code over there should take you to my V card if you're a iPhone or Android user. Add me on LinkedIn. Happy to share this whole prezo with you, or we can talk offline about that as well. You've seen this slide or a variation of it. You're going to see it approximately 800 more times over the next 2 days. So you at least come away from this knowing about US Signal. So US Signal is a cloud service provider in the States. We've got 16 data centers. As John mentioned, we've got edge and micro edge sites coming up, 10,000 or so miles of fiber in a national footprint, really, in commitment to build much more. So we are a service provider. We do a lot in the colo space, very heavy network, and then obviously in the services space. So real quick, I want to talk about the problem here. I've actually had a few conversations this morning, which tells me you all know what the problem is, so that's great. This should be nothing new, maybe unfortunately, but maybe fortunately. The problem is this AI LLM demand explosion, right? All of these graphics are created by AI as well. So unless you've been living under a rock lately, you're talking about it, your customers are asking for it. If you are an engineer like me, your bosses are wanting you to do something more and more with AI. So you likely have been feeling all of these things I'm about to talk about here, right? So as model sizes grow, the compute requirements grow super linearly, which means concave, upward trajectory. While things are getting more efficient from a GPU standpoint, the model sizes are just outpacing the actual compute demands. So the compute demands are much higher. And then kind of like John mentioned this morning, we're of huge belief that inference is really going to be the scaling challenge. So training is very difficult, very power intensive, very hungry, very capital intensive from a GPU standpoint. But inference is only going to be continuous growth and cost after deployment. So training tolerates much higher latency, inference does not. So that's where the edge and super micro edge comes into place. And then compute and power is on the rise. So computational power that's required for sustaining AI's rise is doubling roughly 100 days. There's an interesting factoid here that I'm not going to look at, so I'll try to represent it as best I can remember. But basically, by 2028, they're saying that AI's power demand is going to meet that of the country of Iceland in 2021. So the power is just absolutely crazy, and that's a few of the conversations I've had this morning already is just about that power consumption. Here's a graph showing you that I'm not crazy or making things up. So this is basically the number of parameter model and the training computation required from 2010 to 2020. So notice the 10 billion at the top left and the 100 billion over here on the bottom right. And then this is 2020 to 2025. So our axes are much different to the tune of about 100 times, right? So now you've got 1 trillion all the way over to the right and 100 billion up top. And this is just the model sizes that we're seeing in the environment in the last 5 years. So that is to say, there is no contest that the models are increasing and that the compute demand is also increasing. And the global power problem, right? So AI's demand for power represents over 54% of the total power in the data center space right now. And that's projected to go up to about 71% by 2030. So if you are in the data center space and you're running traditional compute workloads, co-location, network things, they're saying the AI is going to be consuming 70% of the power in that data center space globally by 2030. So that's the problem. Sustainability, power, model size is getting huge. GPU innovation is phenomenal, and they're doing better things every day, but it basically doesn't outpace that computational need. So what US Signal is doing to answer the demand that we're seeing in the market from our customers, from our managed service providers, our enterprises, we did an evaluation on GPUs and high core count Ampere hosts. So I will call out, this was not evaluating a bunch of GPUs, right? You can go on the internet, you can probably ask AI and it will give you something that compares all the different GPU models. So we are testing the NVIDIA L4 for this specific, for the graphs I'm about to show you, and then a couple different Ampere models. So we've got the Ampere 1 Metal, which is a bare metal variant. We've got Ampere Plus GPU, Ampere 1, the Ampere Ultra, and then some traditional x86 workload and x86 workload with GPU installed. So the tests that we're doing from a benchmarking standpoint, these are all the models that will make an appearance. I'm not using all of these models for every single graph, so we'll be sure to call it out. But basically, we're taking very small specialized model up to about a 14 billion parameter model, and we are basically looking at the performance to try to find the sweet spot for your performance per watt, right? As a service provider, that's kind of what I've been tasked to do. And then from a testing standpoint, so we're running a prompt processing test, a token generation test, and then time to first token. Those are pretty standard AI benchmarking tests if you're doing any of this. From a batch size perspective, we're doing between 1 and 64. Each of the graphs is slightly different, so I'll explain those when we get into those. From a thread count perspective, we're doing all cores. We feel that matches production use cases for the most part. You're fully utilizing these as much as possible. Doing 3 repetitions to make sure that we don't have any weird data. Obviously, if I ran one data set and showed you those numbers, that would feel disingenuous to me, but I also don't have the time or money or need to run 10 repetitions. And then from a GPU offload perspective, largely doing 0% and 100%, but there is one graph that I found interesting that I included that is basically doing different variations of GPU offload from a percentage standpoint. And I'll talk about that one because I find that data interesting. So, believe it or not, that was just me laying the foundation, right? So now we're gonna go over the actual graphs. I'll try to be pretty quick with these so that we can get to what US Signal's actually doing based on the data that we found. So first up, we have a tokens per second by batch size. So down here on the left-hand side, those are different batch sizes, 1, 2, 4, and 8. And this is the prompt processing and token generation collapsed. We're looking at the Ampere plus GPU, traditional x86 plus GPU, traditional x86, 96 core, Ampere 1, 96 core. When I say 96 core, that's a single VM with 96 cores allocated. The Ampere 1 with 128 cores, and then the Ampere 1, which is 2 VMs with 96 cores. So interestingly enough, the Ampere 1 with 128 cores assigned to a single VM, we found anything over that, you basically get worse performance. So maybe a KVM scheduling issue. I'll probably end up talking to some people the end of this week about that. But effectively what you see, which is probably not shocking, that when you have a GPU installed, your tokens per second goes up substantially, right? Now, the x86 workload and the Ampere 1 96 are pretty similar. The Ampere 1 128 and the 96 by 2 is a little bit higher. Once we start looking at some of the graphs on power consumption, these numbers look a lot better, right? It's really hard to collapse the two graphs together, but basically what you'll see is Ampere 1 does just as good from a performance standpoint, but doesn't consume tons of power, right? So it's dropping your cost per token very low. Here we've got time to first token by batch size. So again, looking at the same workloads that we called out earlier. And again, with GPUs installed, by no stretch of the imagination or shock, your time to first token is much lower. Your x86, your Ampere 196, and your Ampere 1 128, all very similar. And then the 296 by 2, a little on the high side, that, like I said, that is 2 VMs running virtualized and doing the test simultaneously. So the Ampere 1 with 128 cores assigned, that's the lowest time to first token with not a GPU installed, but again, no shock. The GPU installed drives that time down pretty significantly. Another look at time to first token. So this is looking at a couple different models, right? So our previous models, we were looking at the Llama 3.1. It's actually 8 billion batched bench model. Here we're looking at your Llama 1 billion, your Llama 7 billion, Llama 13 billion, and Qwen 2 14 billion models. And here we're looking at predominantly just the x86 and just the Ampere 1. So here you can kind of see the scale of how this changes as the model changes. The smaller model that you can run that is maybe more specialized, you're gonna have that time to first token much, much faster. The larger models are going to take much longer to get you that time to first token. And this will make sense when I tie it together after all the graphs, right? You're thinking, Daven, this is just data, this is dumb. I will tie it all together. Another look at time to first token. So here we're looking at the 1 billion parameter Llama model and the 7 billion parameter model, x86 Ampere 1, but we're looking at different GPU offload, right? So what this graph shows you is you are almost better off not having a GPU and doing 0% offload than if you do 25% or 50% or 62% offload. So if you're going to have a GPU there, do 0% or 100% and basically nothing in between, or you might as well not even buy a GPU. Our average power consumption by platform. So your traditional x86 is the highest power consumption. Ampere 1, 96 by 2 is lower than that, and then it kind of scales on down, right? I think there's an Ampere talk happening right now at the same time, and this is their claim to fame, right? They're very light on the power consumption standpoint, and they're spec built to be exactly that. So, but can confirm, doing all of these tests, we basically took a look at power across doing all these tests and averaged it out over time. So this is not architecture, this is actual real data. And that Ampere plus GPU consumes the smallest amount of power. Tokens per watt by batch size. So we're taking the tokens graph and the power graph and slamming it together as best we can. So you've got your workloads with GPU, so your Ampere plus GPU and your x86 plus GPU. From a tokens per watt standpoint are going to have the highest tokens per watt because they're the lightest from a power consumption standpoint because of the GPU offload. But what is surprising is the tokens per watt of the Ampere 1 96 by 2. That is very high performance from a tokens per watt standpoint for not having a GPU installed. It is better than an x86 workload with that same GPU installed. Obviously, your Ampere plus GPU, you're getting the best bang for your buck, but your buck's a lot higher, right? Because you have a GPU installed. So the Ampere 1 96 by 2 is really interesting in this graph from a tokens per watt standpoint. Our cost per million tokens by batch size. So here we took like 10-cent kilowatt hour basically to try to graph this out. So your Ampere GPU and on the far right side, your x86 GPU, your cost per million tokens by batch size is the lowest, again, with a GPU installed, and the tokens per second is gonna be much higher. Your Ampere 1 96 and your Ampere 1 128, pretty similar, I would say, and then your x86 workload is going to be your highest cost per million tokens by batch size based on power consumption, and then that token generation. Max CPU temperature by architecture and batch size. So Ampere 1 actually burned the hottest, which is also kind of their claim to fame. If you go talk to them, they'll tell you, you run them hot, you run them hard, and that's what we made them to do, basically. The Ampere GPU and the x86 GPU, your lower temperatures with that GPU offload. And then the x86, not at all surprising. The power impact of running something hotter is something that should be studied probably, but we're not talking about a whole lot of temperature change here in these graphs. All right, so the next few slides are specifically calling out what it looks like when you use an optimized model, right? So this is Ampere 1 workload looking at the traditional Llama 8 bill batch bench and the Ampere 1, the optimized model. So you can see with just some amount of optimization, your tokens per second, literally nothing else has changed from a hardware perspective. It is just optimizing that model for the processor, you get much more performance out of that. I've talked to Ampere about exactly what they've done. They've sent me a write-up on it, but obviously some of it's secret sauce as well. Average power consumption by platform. So again, taking a look at the same piece of hardware, but running a more optimized model. Pretty large difference in a power consumption standpoint when you're optimizing a model. And again, I'll tie this all together on why this is important. And then your time to first token, much lower when you're using an optimized model, right? So what does all that mean? That was a lot of data. That was a lot of Daven talking. Daven's mouth is dry. Lot of talking. So what is the solution in all of this, right? So right use case, right hardware. So we say this in a lot of different ways in many different PowerPoints and summits that we do. It's really about using the right piece of hardware, the right piece of software, the right solution for the right place at the right time. We believe this is even necessary from a cloud perspective, right? We have customers that are using Nutanix. We have customers that are using VMware. Obviously, open cloud is a huge push for us, but really it's all about putting the right thing in the right place. So what that means from a high core count perspective versus GPU perspective, your traditional AI models and small language models actually benefit a lot from just running on AI optimized CPUs, like Ampere, for example, that large banner over there. And then your LLMs, your truly massive models, are always going to benefit from a dedicated processing unit of some kind, right? And we talked a little bit earlier about domain-specific integrators, so like your TPUs and NPUs and IPUs, and we'll talk a little bit more about those as well. But really, some combination of all of those things is what's going to get you the best performance. So we're seeing a lot more use cases in the small language model standpoint, even internally. I would say our AI play is more on the medium-sized model and not the super large 200 billion parameter models or anything like that. Whoops. So what we are doing. So US Signal's path. So last year, as John mentioned, and David will mention, and the other people that I'm here with will also mention, we came here last year talking about Cloudstack and open cloud, right? Which is our variant of Cloudstack. Open source hypervisors. We are pushing this into every corner and crevice and crack at US Signal right now. There's obviously a whole talk you could give on the flexibility of open source hypervisors. We are at Cloudstack conference after all. Hopefully that is not something I need to tell anybody about, but if you do want to talk about that, you can probably throw a stone and hit somebody that can tell you about why you should be running an open source hypervisor. So we did that last year. This year, last 6 months or so, we have been working with ShapeBlue on the GPU as a first class citizen. So vGPU and time slicing is going to be big to make sure that we get the use out of the GPUs that we do buy for our customers, especially as a service provider. For us, we want as much utilization as possible. We need to fit all those pieces together to make sure that we can provide a good service for our customer, but also that, you know, I, who run infrastructure, I'm not asking for $50 million and then stranding a bunch of resources out there that can't be utilized. So this one's super interesting. This has been big in the community the last couple months. I think it's out in 422. So that's going to be a lot of fun probably in the next month or so. And you saw it on John's roadmap this morning. High core ARM 64. So partnership with Ampere. We are deploying our first Ampere-based cluster here in the next month or two. And that is going to be coming to market probably before the vGPU time slicing and GPU as a service, but that is going to be either or will be a fast follow of the other one effectively. And then containerization, right? So obviously there's some native support there. Containerization is going to allow you to use that high core footprint and surface area and do a lot more from a scheduling and consumption standpoint. And all of these things together is what, this is the slide that ties together all the graphs we were looking at, right? Because it is all of these things added together that we're going to go to market with effectively to make sure that we're providing what a customer is asking for. Putting the right workloads in the right location, you know, if it's a small language model or even a medium language model, if we can put that in our high core ARM64 cluster, use an amount of GPU and time slicing, help them containerize their applications and workloads. This is really going to keep the price point very nice for the customer. It's going to keep our costs down. We're going to utilize the hardware very well doing something like that. And then from a sustainability standpoint, I think we've heard about this a few times. I've had a few conversations about this already. It's on the top of everybody's mind. If you're an infrastructure provider, if you're just a consumer OpEx model from people like me, just know that I wake up in a cold sweat in the middle of the night about power. And thankfully, you don't have to think about that. But sustainability. So liquid cooling is becoming more and more prominent. So there's obviously some energy savings there compared to air cooling. We do have a data center that does have some direct-to-chip liquid cooling, and that's pretty neat from an innovation perspective. Committed to dropping that PUE, that power usage effectiveness number, down as low as possible. Really, the liquid cooling is going to allow higher density racks. I don't know when we're going to need 80 kW plus possible racks in the near future, but it's something that we need to think about now, right? So square footage in a data center, unless I buy more data centers, which I do plenty of that as well, I really need to pack that in as tight as possible. Renewable energy tie-ins. So solar farms, windmills, hydroelectric are the fastest growing power source in DCs worldwide. Traditional fossil fuels, though, provide the most stable power flow needed in our industry. So some innovation around the storing of renewable energy for more constant flow, I think, is going to be really important. And then is the future nuclear? So stateside, where obviously there's a lot of conversations around nuclear power right now. I'm assuming it's probably the same over here. But that is a potential for dealing with this power crisis as well. And then just more innovation in general. So GPU innovation is constant. I think you also can't throw another stone in the internet and not hear something about the next GPU being worked on or the next one that already came out, right? So I think GPU innovation is going to be big, but it is not outpacing the model size or the compute demands. That's the problem, right? So even if the next GPU is twice as efficient as the last one, the model's 10 times bigger, right? So it just never outpaces the amount of power needed or how quickly the models are growing. Domain-specific accelerators, so your TPUs, NPUs, IPUs, so your neural processing units, your tensor core processing units, all of that stuff is getting more and more prevalent. We're seeing and talking to a couple of different people to partner with that use those specific chips to do very specific things. And we'll talk about that here in a minute. ARM64 adoption, so we're seeing a lot more of this in the space, even from a public cloud perspective. I think that's going to continue to grow. And then advanced scheduling. So I was talking about this earlier. There's a couple neat projects out there right now that take carbon aware performance per watt and carbon impact into account to do the AI scheduling. I think you're going to see more of those, I think, from a sustainability standpoint. So EcoServe, Slit, and Carbon Call are the three that I was looking at. So that's taking your carbon impact into account when it's doing your AI scheduling. I think we'll see more of that. And then, so the next or current wave. So this is kind of the domain-specific accelerators that we were talking about. You've got the specific accelerators are really, really good from a performance per watt standpoint and from a cost perspective at doing a very narrow scope of things, right? And they're all slightly different. So I've got IPUs and NPUs up here, but if you just Google processing unit, you can get a chart that looks very similar to this. And it's basically A through Z PU, right? Like there's every letter right now that they're coming out with. So specialized processing effectively. GPUs, in, I would say this era, but it's not even this era, in the last couple of years have been that specialized processing unit, but it's going to get more specialized effectively. I think you'll see CPUs more relegated to handling the orchestration, right? Because there's still a lot of x86 out there. There's a lot of legacy items out there that CPUs are going to be really good at orchestrating. And then GPUs and domain-specific accelerators are really going to get more and more prominent, I think. Closing remarks. So AI LLM workloads are reshaping infrastructure demands. Like I said, if you don't know this, this must be your first day in IT. So welcome to the community. GPUs and ARM64 CPUs provide a significant performance per watt advantage. Like I said earlier, happy to share this whole presentation. I also have all of the raw data as well. If you like crawling through a bunch of raw data, you can make your own pivot table, and it'll show you something similar to that. Hypervisors, vGPU, and containers are going to increase efficiency. Again, any one of those things, you can't go wrong. All of those things together, though, is where you're really going to be able to fine-tune your dollar, right? Or if you're providing it for a customer, your cost and spend. Power and sustainability are going to continue to be defining constraints. We were just talking about this morning. It's not going away, right? People are buying up data centers at an increased rate. That's not going to go away. Once all the big cities are gone, they'll come to the little cities and they'll buy up all the space they can as well. So those are going to continue being constraints until we see more innovation in the space, or like I said, some of that advanced scheduling. Hybrid infrastructure and smart software is really going to be the path forward. So again, the combination of all of those things together is really the only way you're going to be able to move forward. Any one of these things are great, fantastic. You're thinking about it, you're moving in the right direction. But if you want to make the most impact, it's going to be all of these things at once. So, of that slide, she bullied all of us. Please go fill out this survey. She told me she was going to break my legs if 170 people didn't fill this out. So, fill out the Cloudstack user survey. Let us know what is going well. Let us know what's not going well. This is going to be super important, but thanks for coming to my TED Talk. If you want to see a lot more data, my boss is smiling at me. I've got like 10 times this. This is the small amount of data. So, but if you'd like to talk more about this, catch me at the booth. Catch me later tonight at the party. If there's a nearby tattoo shop, I'm the tattoo donor that John was talking about. So may get a cloud monkey tonight. We'll see. You're more than welcome to watch, but yeah, otherwise appreciate everybody coming. Hopefully you learned a thing or two and we can talk more after this.